Hello everyone, and welcome to a one-dimensional projectile motion example. So before I do an example here, I want to discuss a little bit, or review if you will, projectile motion. Projectiles, of course, are things that only have gravity acting on them. And that's true on the way up, that's true at the highest point, that's true on the way down. Right? And we're going to neglect all air resistance effects here. Since gravity is the only force acting on them, and since gravity is constant near the surface of the Earth, the resulting acceleration is uniform. And in fact, it's not just any uniform acceleration, it's our old friend negative 9.8 meters per second squared. So on the way up, it will slow down 9.8 meters per second every second. On the way down, it'll speed up 9.8 meters per second every second. Since it is a uniform acceleration, we can apply the kinematic equations. Now I am using these with slight variations. I've changed the horizontal position x's to vertical position y's. I've changed the a's, which is a generic acceleration, to our specific free fall acceleration, negative 9.8 meters per second squared. And I've added these y's to our velocities so that we remember that this is a vertical motion, to distinguish it from two-dimensional projectile motion that we will do in a few days. So today I want to do an example with you and kind of show you how we're going to use the kinematic equations and a few tricks that will help you use them correctly. So first of all, here's our problem. For some reason, a minivan is going to fall off of a 221 meter tall building. I don't know why it's up that high, but it is. So part A, I want to know what is its velocity as it hits the ground. Now careful here, I don't mean its velocity after it hits the ground, which would be the very boring zero. I mean as it gets to the ground, so just as it gets there, if you want to think of it a millimeter before it hits the ground. So it's fallen the entire 221 meters, but hasn't actually impacted the ground yet. That way, it's projectile motion the entire way. So just like with any uniformly accelerated motion problem, we want to ask ourselves two questions to help us set up the problem. First of all, what do you need to know? Well, we want to know the velocity as it hits the ground. This, therefore, would be the final vertical velocity, Vy, right? Not Vo, Vy. Second question you want to ask yourself, what are you given in the problem? Well, first off, there's one number in here. Right? This would be the distance that it would fall. Now, be careful here. This is the vertical displacement. What direction is it going to fall? That's right, down. And so the vertical displacement is negative 221 meters. If you want to think of it here, this is final minus initial position. So your final position would be 0, the ground. Your initial position would be 221 meters in the air. So you're going to have 0 minus 221, a negative 221 meters. It's important to get these negatives in there, as you're going to see in the equations. Now, that seems to be the only number. But there's a couple other ones we can read into the problem. First off, if it just falls off the building, its initial velocity would be 0. And then the second thing is, I think it's a pretty good assumption, because a minivan is a very heavy thing, that air resistance is not really going to affect it much. Sure, there'll be some, but even with a little bit of air resistance, the heavy weight of it will make that really predominate, and therefore it will act as if it is projectile motion. And therefore, the vertical acceleration is negative 9.8 meters per second squared. So, knowing that we're looking for the final velocity, and we know the vertical displacement, the initial vertical velocity, and the vertical acceleration, we can choose a kinematic equation. Since we don't know time, there's really only one to use, and that is the fourth kinematic equation. Final vertical velocity squared equals the initial vertical velocity squared plus 2 times the free fall acceleration times the vertical displacement. Now, the initial vertical velocity is 0, so the initial vertical velocity squared is 0. So we're left with vertical velocity squared equals 2 times g times the displacement. So I want to find the final vertical velocity, so I need to take the square root of both sides. But be a bit careful here. This is vector algebra we're doing. And so directions here are important. So think about taking the square root of both sides. When you take the square root of something, what do you get? Think about it this way. If you take the square root of 9, What's the answer? Hopefully some of you are saying, well, there's two answers. The square root of 9 is 3, but it's also -3. Right? You can get either one. And it's the same thing here. Technically, this is the positive or negative square root. So which one do we use as our answer? We use the one that makes sense with the problem. Since we're solving for the final vertical velocity, and the minivan will of course be moving down at that instant, we need to use the negative result. So I've plugged the numbers in here, and notice we have a negative 9.8 and we have a negative 221 meters. Now, if you had missed the negative, and the common one to miss here is the displacement negative, notice you would get a negative under the square root sign, which would give you an imaginary number. And although I completely made up this problem, I want a real answer. So we can't have a negative underneath the square root. Right? So that would be a hint that you have to check your negatives here. Right? So two negatives will cancel. Take the square root, make the answer negative, and you get a negative 66 meters per second. Now, since the conversion factor is about 2.2 to get to miles per hour from meters per second, you're talking a good 145 miles an hour downward when it hits the ground. So that's pretty darn fast. That's going to hurt. So as you're falling, knowing now that you're going to hit the ground at about 145 miles an hour, you may wonder, just how long do I have before I hit the ground? How long am I going to stay in the air? So of course what we're trying to find here is time. Second question, what are we given? Well, we have the same givens as before. We know the vertical displacement, we know the initial vertical velocity, and we know the acceleration. Now we also know the final vertical velocity, but remember, it's always good, if you can, to not use something you just found. That way, if you got part A wrong, you won't get part B wrong. And in this case, we don't need the final velocity because these three things and the time are related in the third kinematic equation. Now this one can get quite difficult to use sometimes, but in this case, it's fairly straightforward. Since the initial vertical velocity is 0, 0 times the time is 0. So we're left with vertical displacement is 1/2 gt squared. Move the 1/2, multiply by 2. Move the g, divide by g. So there's multiplying by 2, divide by g. And now we need to take the square root. Now technically we get the positive or negative root, but it's time. Time only runs in one direction, so we want the positive answer. Plug in your numbers. Notice again the negatives cancel here. If you had missed the negative sign on the displacement, you would have gotten a negative under the square root, which should set off some bells so that hopefully you get the negatives correct. Lots of negatives to keep track of in projectile motion. Work your calculator, you get a time of a large 6.7 seconds. So you have 6.7 seconds to think about what's going to happen before you would hit the ground at roughly 145 miles an hour. So I hope you've enjoyed this little example of one-dimensional projectile motion.